Have you ever wondered how these massive online services we use every day can handle just an incredible amount of data without completely collapsing? Well, it's not just about throwing more servers at the problem. It's actually about how cleverly they organize and then find all that information. Today, we're going to dive into two of the most important concepts that make it all possible: rebalancing and routing.
So let's kick things off with a question I'm sure we've all felt. You're on a huge website, you know they have thousands of servers, but for some reason, everything is just sluggish. Why does that happen? Well, the answer has everything to do with how data gets organized, and more importantly, what happens when it gets disorganized.
You see, the heart of the problem is something we call a skewed workload. The best way to think about it is like a supermarket with, say, 20 checkout lanes. Now, if every single shopper decides to line up at just one of those lanes, it doesn't matter that the other 19 are totally empty. You're still in for a very, very long wait. In a data system, we call this a hotspot, and it's where one server gets absolutely hammered with requests, creating a massive bottleneck for the entire system. So how do we fix these hotspots? How do we get those other servers back to work? The solution is a really elegant process called rebalancing. You can think of it as the art of intelligently shuffling the workload around to keep everything running nice and smooth.
So what is rebalancing, really? Well, it's the process of moving data and all the requests that come with it from one machine or node to another. And this isn't just a one-and-done kind of thing. No, it's a continuous process that's absolutely essential whenever the system changes, like when you add new servers to handle more traffic, or, when a machine fails and its neighbors have to pick up the slack.
Now, any good rebalancing strategy has to play by three golden rules, no exceptions. First, the load has to be shared fairly across all the servers. That's the whole point, right? Second, the database has to stay online and keep serving requests while all this shuffling is happening. You can't just put up a "closed for cleaning" sign. And third, and this one's a biggie, you only move the absolute minimum amount of data you have to. Why? To keep the process fast and to avoid totally clogging up the network.
All right, so we get what rebalancing needs to accomplish, but how does it actually work under the hood? Let's take a look at a few different strategies, and we'll start with a really simple idea that, spoiler alert, has a pretty massive flaw.
So a common approach uses a little math trick. You take a piece of data's unique ID, or key, you run it through what's called a hash function to get a number, and then you use the modulo operator with the total number of servers, which we'll just call n. So, if you've got 10 servers, hash of the key, mod 10, is going to give you a number from 0 to 9. Simple. Now you know exactly which server is supposed to store that piece of data. Seems predictable, right?
But, and this is a huge but, here is the massive, show-stopping problem. What happens when n, our number of servers, changes? Let's say we add an 11th server to handle more traffic. Suddenly, our formula changes from mod 10 to mod 11. And the result? It's a catastrophe. Almost every single key in the entire system now maps to a completely different server. This triggers a frantic, system-wide data shuffle. It's wildly inefficient, and it makes this simple idea pretty much unusable for any large dynamic system.
Okay, so if mod n is a disaster, what's a smarter way to do this? Well, the answer is to decouple the data from the physical servers. You do this by creating a fixed number of partitions, way more than the number of servers you actually have. Just think of them as virtual buckets for your data.
And this slide shows the solution perfectly. Look at the before state. We've got 4 nodes, and they're sharing all the partitions between them. Now, watch what happens when we add a 5th node. Instead of that total meltdown we talked about, the new node just steals a few whole partitions from the others. See how only a few of those little blocks move over? It's surgical, it's clean, and it's way, way more efficient.
And believe it or not, the strategies get even smarter from here. With something called dynamic partitioning, the partitions themselves can automatically split in half if they get too big, or even merge with a neighbor if they shrink down. Proportional partitioning is another cool take. It tries to keep a fixed number of partitions on each node. So when you add a server, it'll automatically split some existing partitions to keep that ratio. Both of these just offer more flexibility for different types of data.
Okay, deep breath. So we've brilliantly organized our data across all these servers. The load is perfectly balanced, those nasty hotspots are gone, but wait, in solving one problem, we've actually created a brand new one.
Just think about it for a second. With our data now scattered across hundreds, maybe even thousands of different machines, how does your request for, say, your user profile know exactly which of those machines to talk to? This is the whole new challenge of request routing.
So let's unpack how systems actually solve this. There are a few really common strategies for getting a request to its correct destination, and you can kind of think of each one as a different type of GPS for your data.
The first approach is pretty straightforward. The client just sends its request to any node in the whole cluster. It's a guess. If it picks the wrong one, like node 0 here in the diagram, that node is smart enough to know where the data really lives, and it just forwards the request internally to the correct one, which is node 2. It's kind of like asking a random person on the street for directions, and they actually walk you right to the front door.
Approach 2 is a little more organized. In this setup, every single request first goes to a specialized routing tier. Now, this thing doesn't store any data itself. Its only job is to act like a traffic cop. It looks at the request, it knows exactly which node is responsible for that data, and it sends it right there. This model is super common in modern systems because it keeps all the other services simple.
And then there's this third approach, which is the most direct of them all. Here, all the intelligence gets moved right into the client itself. The application that's making the request has its own map of the cluster and knows exactly where everything lives. You see this a lot in super high-performance systems where cutting out that middleman hop saves precious milliseconds.
Okay, but this leads us to the final and absolutely critical question. Whether you have the traffic cop or the smart client, how in the world do they keep their maps of the data up to date, especially when rebalancing is constantly moving those partitions around?
And that brings us to the final piece of this entire puzzle, a coordination service, like Apache Zookeeper. You can think of Zookeeper as the ultimate source of truth for the whole cluster. It maintains the master map of exactly which partition is on which node, right down to the specific IP address. All those routing tiers and smart clients, they subscribe to Zookeeper, and whenever a partition moves, Zookeeper immediately notifies them so their maps are always current.
So let's just take a step back and put all these pieces together. You can really see it's this delicate, intricate balancing act between organizing your data efficiently and then being able to find it in a split second.
So let's just recap that journey real quick. We started with hotspots, right? That problem of uneven workloads. We solved that with rebalancing, which intelligently shuffles all the data around. But that created a new problem. How do we find the data now? And we solved that with request routing. And the glue that holds the entire system together is a coordination service, like Zookeeper, providing that master map for everyone else.
And that really brings us to our final thought. We've seen how these incredible systems work today, but as the amount of data in the world continues to grow at this exponential rate, what do you think is the next huge challenge in managing and finding information on a truly global planetary scale?
If you found this explainer helpful and maybe demystifying some of the complex tech that runs our world, do me a huge favor and be sure to hit that like and subscribe button for more deep dives. Thanks so much for watching.